Thank you. Thank you. I am Bálint Tóth from the University of Pannonia. I'm a PhD student in computer science. And as we are approaching the end of the GPU day, let's turn our attention to GPU programming, uh, specifically the technicalities of Fourier transform computation on NVIDIA GPUs. Um, yeah. So in this talk, I would like to briefly introduce some limitations of cuFFT and talk about the new cuFFT device extension and introduce some of the C++ metaprogramming techniques used to achieve its interface and give you a short example. So how do we compute Fourier transforms on the GPU? Well, there is the obvious answer. We use the built-in FFT library of CUDA, which is cuFFT. Option B is, of course, we implement it ourselves, but that's never going to be that fast as the cuFFT implementation because it is an official NVIDIA tool. They basically have full-time personnel working on that. We are just not going to reach its performance. And it is very simple to use. It is basically created to transform host-side computation algorithms to GPU codes, basically. The first thing is that you create a plan, which is a description of a Fourier transform, copy the data to GPU DRAM, so global memory, execute the transform, and after the transform, put your memory back to the global memory, and then copy the data back to the host, which is, well, there are some problems with that. Namely, what if we want to do some very simple one of operations before and after the Fourier transform? Well, the naive approach would be to use a separate GPU kernel, but that's just terribly inefficient. The preferred way is to use the device functions or device callbacks, which are basically CUDA device function pointers that can be supplied to the library. They have the following signature, and they execute during load and store. These are, in my opinion, not quite sophisticated, quite primitive, to be honest, because there's a limited number of operations we could do with it. Um, they are they are just acting on a single element, and the logic still has to be on the side of the host code. So the whole algorithm just couldn't run directly on the GPU. And of course, they use the very best practice void pointer, which definitely is not the cause of many memory corruption errors. So for this, a new library was introduced by NVIDIA around 3 years ago, which is still in development. It is part of the MathDX library package, which is the mathematics device extensions. It now currently supports cuBLAS and cuFFT and provides highly optimized solutions for Fourier transforms and, of course, BLAS routines that are callable directly from GPU code. And they are configured with this embedded domain-specific language inside C++. Now, this is the part where I would end the talk. That's it. Very simple. We can use it. But this method of configuring a transformation in compile time is, I think, very kind of could be useful for many other applications for reasons I will talk about later. So I would like to introduce some tricks used to achieve this. The first one is C++ template metaprogramming, which is, well, an accidentally found Turing-complete programming language inside C++. Basically, templates are a way to implement generics, and as can be seen on the following source code, it's very simple. We just create a type parameter, and inside our own new type, we just use that for the declaration and definition of the type. And when we want to use it with a specific type, we specialize it, where the parameter gets substituted in place of the type parameter. Now, in of itself, this is basically the intended use of this language feature. The unintended use of this language feature is that with the use of partial template specialization, where we could specify what kind of implementation we want for a specific template argument, we could do arbitrary computation during compile times. With the simple example, it takes a predicate and two types. If the predicate is true, it returns the first type, and when the predicate is false, it will return the second type. This is basically an if statement that is handled by the compiler. And using constant expressions, we can create various recursive functions, for example, this factorial. I couldn't really think of a simpler example, to be honest, but this is basically the syntax of calling a meta function. And the second concept I would like to introduce to you is expression templates. Now, the cuFFTDx documentation doesn't really go into the details of how their API is implemented. They just say that, oh yes, we are using a special version of expression templates, which are basically a way to decouple computation from an expression. And implement what is known as lazy evaluation. Now, normal eager evaluation, like standard C++, is very simple. The compiler will basically generate code that evaluates runtime the mathematical expression and calls the function on the result of that expression. A lazy evaluation, on the other hand, we do it we have basically the same syntax, but under the hood, we build an expression tree, and we put the expression tree into the function without evaluating the result of said expression, meaning the function can decide whether or not to modify the expression and when to evaluate it. This can be done by simply implementing the nodes of the expression tree. So this is a leaf expression. It's a constant that when evaluated returns the constant value. This is a binary operation that encodes a left-hand side, a right-hand side, and a binary operation. And it basically returns upon evaluation the operation on the left and right-hand sides evaluated values. And this is how we can basically abuse operator overloading to produce these binary operation structures. Now, why did I bother telling you all of this? Basically, cuFFTDx uses operators, and as can be seen, this kind of configuration language looks really similar to the one I introduced previously. We have a bunch of plus operators that basically assemble into something. And by using decal type, we actually deduce the type of the result of this expression without evaluating the expression, meaning we have a compile time something that can actually do Fourier transforms. And it is achieved with these concept of operators. Basically, we have a type class that is the alphabet of our domain-specific language, and elements of this alphabet are implemented as specific operators. These are just simple structures that encode a single value as a constant expression that is given to them in compile time as a template argument. Of course, in real cuFFTDx, it doesn't look like this because that would just overcomplicate this whole example. But under the hood, it's something like this. And the other one, which kind of ties together these operators, is a trait. Now, traits are widely used in C++ standard template library. They are even turned into a language construct called concept. And with this, we can later do the pattern matching step that will reverse this very complicated kind of description struct. It is basically a function. It takes the operator's type, i.e. which element of the alphabet we are looking for, and the type itself, which is the operator, and it's used here. Now, this is basically the entire configuration of a transform. It takes a variadic amount of operator structures, that are configured previously by templates. And with these getter meta functions, which are actually just types, I will show you how it looks like on the inside. It can query from this list the actual element, the type that encodes a specific operator or specific element of the alphabet, and then we can just query the value. This is done with this very ugly function or type, basically, which uses the previously mentioned operators and pattern matches um, uh, the argument list, the variadic argument list. And to create the variadic argument list, as we saw previously with the plus operators, we use this kind of abusing of the language to mesh together several argument lists into a single one. And when we call decal type on the result of this kind of description, we will end up with a single type that has in its parameter list all the operators that describe a transform. And this is basically that part of the whole story. We can now configure a transform, but how do we actually execute it? In a talk yesterday, it was mentioned that using high-level abstractions is not a very good idea in high-performance computing and in GPU programming, because it will basically add in unnecessary operations in very time-critical applications and algorithms. How did they achieve the quite opposite? As we will see, it is actually on par with cuFFT, sometimes even faster. Well, they have the complete description of a transform in compile time, of course. We still haven't executed a single line of code. It is then put into an execution structure that communicates with, well, a database of some sort. It is a directory of include files and pre-computed PTX assembly files alongside a whole bunch of FFT twiddles and pre-computed FFT multiplier constants that are just inlined into a method. So basically, the implementation is completely decoupled from the explanation. Hence, we didn't have any kind of serious performance penalty. And this is the main reason I wanted to talk about this, because I think it is a really neat technique that could be used in other areas where a high-level interface is needed for a GPU program. Right now, it supports the following description operators like size, direction, type, precision, very standard Fourier transform stuff. These could be queried using these trait functions that take in a description as a template argument and return their value as a constant expression. And we have two execution modes right now, which is block and thread. Now the thread one does, of course, a Fourier transform in a single thread, but with block, we could actually use stride loops and folded Fourier transforms to great lengths, actually. Of course, there are some things that we traded in for this kind of intuitive, easy-to-use interface. Namely, this is a single header-only library. It takes around a minute to compile a very simple application. Now, of course, most of the times we compile once and run many, many times. So this is actually not that big of a deal. It's just annoying sometimes. But in the end, we will have a basically highly specialized for our needs Fourier transforms with a whole bunch of pre-computed values. And of course, the fastest computation is the computation you don't have to do because it is already compiled into your program. Of course, C++ being C++, a very small programmer's error can result in multiple hundreds of lines of error message that doesn't describe the problem, but in turn very, very hard to decipher. The pre-built FFT implementations mean that the longest sequence input sequence on my specific Ampere card is around 32,000, which is not a whole lot, but sufficient for many of our needs. And of course, the kernel's data layout still has to follow the cuFFTDx's preferred way of storing its values in registers and shared memory. And of course, I think needless to say, we have no way of changing any of the configuration parameters during runtime. So I think that's the largest drawback of this whole technology. And I would like to give you a very short usage example, which is Welch's method for power spectral density estimation. It is a widely used DSP algorithm. It is an extension to the classic periodogram because the standard periodogram is kind of very sensitive to noise. And the method proposed by Welch is basically chopping up the input sequence, applying a window like this one on them separately, and then after computing all the power spectra, those are averaged together like this. We basically chop the signal into 3 segments, window them, do the Fourier transform, and an averaging step. Now, basically, this is a point where we actually need the Fourier transform, and of course, many operations are needed before and after. And in theory, it could be done with device callbacks, but for reasons, i.e., it is very hard to do reduction in cuFFTDx callbacks, I chose this DX implementation. Now, basically, the naive cuFFT would look like this. We create a plan, we call a distribution kernel, which splits the data, does the windowing. It is horribly inefficient. Do the FFT, which is optimized to the absolute limits. It's very good, but then we also need to do the averaging, which is, again, a terrible thing to do on its own. And if no other algorithms are around this FFT or this algorithm, we couldn't even fuse these kernels with the previous and next ones. So we are just kind of hopeless at that point. Enter the scene cuFFTDx. We do a simple configuration of a type that we put into a kernel, do the loading and the windowing inside the kernel in a stride loop, do the execution, and then for this example, I left in the atomic odd and the averaging like this because the other one wouldn't fit on the slide. But basically, very similar, the same steps. The only difference is that it's actually in the kernel. We don't need any host side logic for this. And well, why would we do this? So I measured with synthetic data. Our research group does EEG signal processing, so I took some of my old benchmark data for that, which is 128 channels of 2 kilohertz signal from around a minute to 16 minutes. And well, we got around half the execution time, which sounds really good. In 16 minutes, it is very impractical. We don't do this kind of long periodograms, but in 16 minutes, the blocks started to clog up the GPU, so it got a bit worse, but not that terrible. And the main point is that the performance increase. So this is a roofline chart. Basically, this is the boundary of the memory bandwidth and the compute bandwidth of a GPU. And this axis is the arithmetic intensity, i.e. how many floating point operations we do for a single byte of fetched from the memory. And the y-axis is the performance in flops. Now, with the naive implementation, the 3 kernels placed around here, they are severely memory bandwidth bound. As we can see, the cuFFT implementation is literally couldn't get any better, but the distribute and average kernels are terrible in performance. Now, we just got a single kernel that is on the edge of compute and memory boundedness uh, above a teraflop per second, just trivially putting the code from the previous kernels into another kernel in a for loop, which I think worth a while. Yes, and this is basically the end of my talk. I hope I have managed to raise a bit of awareness towards these kind of C++ metaprogramming techniques and how they could be used to speed up, well, not necessarily speed up, but enhance the everyday GPU usage. Um, and I actually had a couple of ideas doing this presentation. The first one is that can we use expression templates as digital signal processing windows for later? Because right now I'm adding them in kernels with templates and function pointers. I just thought that the compiler is really good at inlining expression templates, so this could actually be a source of further speed up. And I'm planning on introducing the same logic to a whole lot of our other DSP algorithms used in our signal processing pipeline. And with that, I would thank you your valued attention. And yes.
We have time for a few questions.
Thank you very much. It's good to see some old-fashioned template recursions now that we have const expressions that are sometimes working and sometimes not. My question is, does it actually work? So I've been doing similar things for 10 years since C++11 is out. It's more than 10 years. And basically, you can compile the example that is on whatever web page or sample code or CPP reference. You might be able to add one extra twist to that. It might work. And when you add the second extra twist, when you are trying to implement an actual problem, what you are getting is compiler crashes, internal compiler errors, front-end errors, miscompilations, invalid code generation, and sort of things like that. And this has been continuously the case since C++11 shipped on each of the widely used C++ compilers, including NVCC. So my question is, I gave up 2 or 3 years ago. That was the case even 2 years ago that we wanted to put together a compile time pipeline with I really kept the template metaprogramming at the bare minimum. We hit a case where it was not possible to work around and we just stopped working with things like that. So have you encountered any of that in your experience?
Yes, indeed, many times. When I was reverse engineering the code, I got internal compiler errors many times. I have actually found out that I mean not found out, found that in certain cases NVCC and GCC like did use these template types a bit different, which for me it's like unexplainable at this point. It was really inconvenient. This is why I was showing these heavily sanitized examples, because like the real one just looks like a bowl of spaghetti. Um, I really didn't do that much template metaprogramming. I just heard of this technique 3 years ago. I think I still haven't hit the boundaries of it. But you mean I shouldn't spend the next 2 years of my life developing a compile time pipeline description using this technique, right?
Yes, so I think it should be telling that NVIDIA has not shipped this into production, if I understand you correctly. It's in development for quite a few time, right?
Well, they shipped it
They shipped
3 years ago, yes, but doesn't really talk about it that much.
I think there is a reason.
Yeah, I know, but for these like niche little algorithms, it's, I think, perfect.
I think the idea is very important, and yeah, we can talk about that later. But
Okay.
yeah, I think there are many dangers in this path. Yeah, thank you very much.
So there is no more question. So I'm giving the word for first. Yes, thanks for the presentation, and I'm giving the word for closing to Gergely.
Thank you very much. So we never thought that the 15th GPU day can be reached. What we have even done with that. We have a few minutes left. But so just let me summarize what happened in these 2 very dense days. So we had more than 60 participants. We have 20 people listening us online. Some of them was also participants. And I think we had a wonderful 2 days with a lot of interesting stuffs. And as you know very well, that you can use our facilities in the future. And if you have projects, we are very happy to host it. And we are working on the other side to have more and more better hardware and software and other solutions. And of course, I mean, they are not already there, but a big thank to the supporters, the Hanrin headquarters, where we are now, and provided this beautiful place. Of course, the Wigner Institute with all of the background support, the Lombic Limited, the 5.9 and the Skyblocks Limited, which gave us the funds for having this event and a nice view. And last but not least, I would like to ask all the organizers you helped me, to Gábor, Zsófi, Anna, Balázs, Ildikó, please come. And I would like to ask you to big acknowledge to them. Please stand up. And I hope you felt that the food and the service was pretty good. So this was thanks to Ildikó and her work. So with this little present, I would like to acknowledge to her all the duties she gave us. So Ildi, thank you again. And I think there's nothing left. So I can just say goodbye and see you soon on the 16th GPU day. And don't forget the lectures in around November, which supposed to be quantum machine learning lectures. So thank you very much and enjoy. Take care.